This bridge stood for 30 years. Then engineers opened up the concrete and were horrified. Inside, it was all crumbling. The rebar had rusted through completely. Millions of dollars are spent on repairs, and this happens everywhere, in every city around the world. But what if rebar could physically never rust at all? Today, let's talk about a material that's changing construction. Let's start with the basics. Concrete is an artificial stone. It is incredibly strong under compression. Put a ton of weight on it, it will hold, but try to bend or stretch it. It will crack just like ordinary stone. That's exactly why concrete is reinforced. Rebars are placed inside to take on the tensile loads. This creates reinforced concrete, one of the main materials of civilization. Houses, bridges, tunnels, dams, all are made of reinforced concrete. Traditional reinforcement is made of steel. It works great, but it has one fatal enemy: water. More precisely, water plus oxygen plus time. In other words, rust. Steel corrosion is not just a cosmetic problem. Rust takes up 3 times more volume than the metal itself. It literally tears the concrete apart from the inside, like a tree seed sprouting through asphalt, only much more destructive. According to the American Society of Civil Engineers, the US infrastructure received a grade of C-, almost unsatisfactory. The cost of repairing bridges and roads amounts to trillions of dollars. The main reason is the corrosion of the reinforcement. In coastal areas and northern cities where roads are salted in winter, concrete structures deteriorate 2 to 3 times faster. Salt is a catalyst for corrosion. It literally accelerates the death of the reinforcement. Engineers have known this for a long time and have long been searching for a replacement. Composite reinforcement consists of rods made not from metal, but from fibers embedded in a polymer matrix. It sounds complicated, but the idea is simple. You take the finest threads, glass, carbon, or basalt, impregnate them with resin, pull them through a mold, and bake them. The result is a rod that is lightweight, strong, and absolutely impervious to water. There are 3 main types. Fiberglass reinforcement is the most common and the cheapest. The fibers are ordinary glass, stronger than steel in tension. It weighs 4 times less. Basalt fiber reinforced plastic. The fibers are made from molten basalt, a volcanic rock slightly stronger than glass and better at withstanding high temperatures. Carbon fiber reinforced plastic. The fibers are made of carbon. It's the strongest of all and also the most expensive. For now, it is used where price is not the main concern: aviation, space, and sports cars. They all have one thing in common: the polymer matrix does not let water through at all. These materials are used in shipbuilding and the chemical industry, places where metal corrodes within months, but in concrete, they can last for hundreds of years. Let's honestly break down what composites actually offer. First, corrosion resistance. This is the main thing. No rust whatsoever. It's perfect for bridges, piers, swimming pools, marine structures, and roads in climates with salt. Second, weight. Fiberglass rebar with a diameter of 8 mm weighs about 4 times less than steel rebar of the same diameter. On a large project, that's a ton of savings. Less load on transportation, easier installation. Third, dielectric properties. It does not conduct electricity. This is critical for MRI centers, power plants, and facilities near high-voltage lines. Fourth, radio transparency. It does not block signals. It is used in airports, military facilities, and telecommunications towers. Fifth, thermal expansion. For fiberglass, it is close to that of concrete. There is less internal stress during temperature fluctuations. The cost is lower than steel. Even now, in stores, a running meter of fiberglass rebar costs less than its steel counterpart. And if you consider the entire life cycle, the savings become even more apparent. It would be unfair not to mention the limitations because they do exist. Composite material is not ductile. Steel deforms before it fails. This is called plastic deformation. The structure gives a warning about the problem. Fiberglass breaks suddenly, without warning. This changes the logic of calculations and requires a different approach to design. The modulus of elasticity is lower. Fiberglass bends more under load than steel does. This is important for beams. A larger diameter or a different configuration is needed. It can't be bent on the construction site. Steel rebar is bent right on site, while composite rebar can only be bent at the factory to order. This is not just theory. Composite rebar is already being used all over the world. Canada is one of the world leaders in its application. There, roads are salted especially aggressively, and bridges with GFRP rebar have been built since the 1990s. Some of them have been in operation for more than 30 years without any signs of degradation. Japan actively uses carbon fiber in seismically active areas. In Europe, it's used for bridges, subway tunnels, and coastal structures. We live in an era when materials created for the aerospace industry are gradually becoming mainstream in construction. Composite rebar is not a silver bullet. It has its limitations and they are real. But for the right applications, humid environments, aggressive chemicals, marine climates, special electromagnetic requirements, it's not just an alternative to steel, it's the best solution. For the next 50 years, infrastructure will be built from different materials. And now you know which ones. Subscribe to the channel and also check out how fiberglass rebar is produced at the factory. We filmed the entire production cycle. The link is in the description.